The slide I'm showing, it's not numbered, but control system components. Can you see the slide?
Yes, ma'am.
Yes, ma'am.
Right. So today we shall be starting with control system components. As you might be aware, those of you who are in the B section, basically you did not attend my class last week, and I was supposed to teach errors and steady state errors and error constants in that class. So I'll take it as if that portion has been done in your section. A section, of course, is going to continue normally. So for both the sections today, control system components is what we are going to do today. So before going into the control system components, let me tell you something that is, as far as this particular part of linear control system is concerned, meaning the part that I'm going to teach, part one, over here, there are quite a few control system components that we will be learning. But because, I mean, if I keep on teaching the components only, I mean, all in a series, it might become boring. So, I mean, basically, some control system components will be done. Then we'll go back to some sort of analysis of systems, again, come back to some other components. That is the way we will do it. So, today, of course, we are going to start with the first or the most sort of simplest component that we are about to study. So you are familiar with this term, I'm sure, in your measurements you would have done in the second years. That is transducers. What are transducers, by the way? Can anybody tell me?
Ma'am, transducer is a device which converts any non-electrical quantity into an electrical quantity.
Okay. Yes, you are correct. In, I mean, up to a certain extent. Basically, there's a more generalized definition in the sense not only from a non-electrical to an electrical quantity, but from one form of a signal to another form is what we say a transducer is. So it may be that we are, I mean, converting from an electrical quantity to a mechanical quantity, namely position, or vice versa, meaning maybe an angular velocity is being converted to an equivalent called a transducer. So a device which does that conversion is called a transducer. So you can see over here, a device which converts a process variable in one form to another form. I'm sure, I mean, I'm aware that you are already familiar with that. Now over here, we are going to actually do some specific types of transducers, which are used as parts of control systems. So basically, that would be the focus of this particular class. So one of the most important transducers essential for control systems is the error sensing transducer. Now, you would recollect that in all that we have done till so far, we have been drawing block diagrams, and in that block diagram, there is a particular portion which we call is the error sensor or error detector. So naturally now, I mean, some physical component would have to be used such that error detection or error sensing is done, right? So error sensing transducer is one of the most common transducers which are used in control systems because we need to compute the difference between two signals and then maybe generate an equivalent signal which is going to drive the plant. So the error sensing transducer is what we are referring to. Now the error sensing transducer consists of two identical transducer elements so connected that they produce an output signal which is generally a linear function of the difference between the two signals at the input of the two transducer sensing transducers. I'll come to that in a moment with the help of diagrams and all. Now, okay. As far as the diagram is concerned, it doesn't show you an error sensor. Right now, we will go to error sensors, but before that, we'll go to something which is known as potentiometers. But because we don't have a diagram, I'll repeat what is being said over here. Basically, there are two inputs to the transducer, and the transducer is going to do the job of comparing between those two inputs and generating an output which is, I mean, proportional to the difference between the two signals. So basically, it's going to generate an output which is a linear function of the difference of the two signals at the inputs. That is what a transducing element, which is acting as an error sensor, is supposed to do. But now we will see physically how such which components can act as such error sensing transducers. So first of all, we come to a component again with which you would be familiar, which is known as a potentiometer. Now, as far as potentiometers are concerned, you can see over here on the left side and the right side, there are two diagrams which are schematically drawn and which indicate the left side is a linear potentiometer, the right side one is what we call a rotary potentiometer. Potentiometer is the short form for it, which is known as this. You can see the left hand side diagram. Directed across over here, this is a resistive element, right? And the voltage is applied across the across this element will be the reference point. So reference point, it may be grounded, would be basically this particular zero. And we have what here is on. Microphone is on. Shamarphone. Okay. So there is a pointer over here, and the pointer you can slide the pointer along this resistive element. Slide the pointer over here. If this is the reference end, this say for example this end is grounded. Okay, so now what will be the voltage at the output? Voltage at the output means from the pointer to the reference point, maybe the ground. Okay, so basically the voltage across this will actually be proportional to the length of the element over here. So if we say that the overall length of the resistive element is say capital X suffix small n, so xm is the overall length of this element, and also it's going to be proportional to the resistance naturally. Now, and now if the pointer is at some general position over here, and the length of the element from the reference end to the pointer is given by small x. So small x is the amount of length that we wish to actually read at the output side, and the maximum possible length of the element is xm, right? So the m actually stands for maximum. So now the voltage at the output side will basically be proportional to this length, because this length will actually be proportional to again the resistance, right? So if the overall resistance of this element is proportional to xm, this portion of the resistance is going to be proportional to this x, right? So we So V, that is the small v, that is the voltage at the output side, is proportional to the length of the element over here, namely small x. So V is equal to some constant into x, small x, right? And now, if we try to see what that, constant is going to be, you can see that the overall voltage which is applied across the whole resistive element is given by E. So capital E by capital XM, that multiplied by small x will actually give us the voltage at the output side, right? So basically, this E by XM is what would be the constant K that has been indicated over here. So now a very simple thing is going to be done over here. By sliding the pointer, we are going to be able to get the output voltage. Now, what is, going to be indicated by the side of the pointer? The linear displacement on this side can actually be, indicated by the changing of the position of the pointer. Let us say, for example, if instead of over here, the pointer points to this point, that means, the length of element now has increased. It's going to be some, say, x2 or something. So naturally now the output voltage will be proportional to that x2 instead of the small x that we have over here. So the linear displacement is directly being converted to an equivalent voltage, and hence, of course, it is a transducer, and this linear potentiometer will give us an output voltage from the, reading of an input linear displacement. The input for this particular system would be the linear displacement, right? So the right hand side now we have a similar diagram which is the rotary equivalent of the linear potentiometer. So on this diagram we have again the source of excitation which is E, and we have this resistive element. Now the resistive element over here is circular in nature compared to the linear, the straight line one that we had for the linear potentiometer. So over here basically the this circular element has a pointer. This is the arrow over here is the pointer. Now say it is fixed at this particular point, and can be this pointer can be rotated such that it can span the angular displacement from this point to that point. So again, there will be a reference end. Let us say that this end is the reference end. So basically this point is what we have. And now, depending on the angular displacement theta, we will get an output voltage V. So V is going to be proportional to the angular displacement theta from this end, where theta suffix small m is the maximum angular displacement, which can be indicated by using this rotary potentiometer, right? So V is equal, small v is equal to some constant into theta, and that constant will be equal to how much? It's going to be capital E by theta m, because theta m is the maximum angular displacement which we can have, and E is the source of EMF. So basically, V is equal to E by theta m into theta. So you can understand that now, if there is a small angular displacement theta from this, when I say small, I mean with respect to the reference end, of course. So if there is a small displacement, the voltage is going to be proportional to that, and we will get that value. If there is a larger displacement, again, we will get the proportional voltage at the output. So the rotary potentiometer enables us to convert an angular displacement into an equivalent output voltage. Now, such potentiometers are used extensively as error sensing devices, but not in this particular form. We have to make a bit of a modification to such potentiometers so that we can use them as error detectors. Okay, this actually is a photograph which has been taken, not exactly a photograph, but half of it you can say it's drawn like a photograph. It's taken from a website and it shows you the, picture of a linear potentiometer. Need not go into too much of details, but it's there with you in case you want to refer to what exactly goes in inside over there. You can have a look. We can of course see over here that the mm, the housing and the washer and the continuity strip and all that. You can see what is there in the inside, that is, as far as the construction is concerned. Similarly, a rotary potentiometer is shown over here. You can see it's actually a circular element like this, and you can see the components which are going to constitute the rotary potentiometer. The reference is given over here. Reference means the website from which these figures or pictures, whatever you call it, have been, taken. It's given over there. You have the slides with you. And if you want to actually see what these are or a bit of details of these, you can see just for your interest, that is. So now coming to how potentiometers can be used as error sensing devices. So here I have not drawn the figure by using a computer naturally. I've taken it from the notes of, you have seen the name of Professor K. Datta. He had drawn the figure. He is, of course, he has expired a long time back, I think in 2016 or so. But anyway, this is his, drawn by it. This was drawn by him in his notes. I've kept it because it has clarity. In case you do not understand something, you can tell me. Otherwise, I have not redrawn it, this particular figure. Okay, these two figures, So now on the left hand side, what you have is you have a pair of resistive elements, as you can see. both are connected in parallel across a source of voltage. So the source of voltage you can see is 100 volts and the polarity has been indicated. And you have two pointers, one connected to this resistance and the other connected to the other resistance. The output now is going to be read from here. So this is the output voltage. So now the output voltage actually is going to be indicating the difference in the readings over here. Readings, by readings I mean the linear displacement and hence the proportional, I mean voltage. So, I mean, over here, the writing has been done in terms of the voltage. So, let us say that the linear displacement over here, this point from this end, is equivalent, going to give you the equivalent of 75 volts. Actually, it's supposed to be indicated in maybe millimeters or centimeters because it is a displacement. But the equivalent voltage has been indicated over here so that you understand what exactly is happening. Similarly, this pointer is pointed at a particular point, which is a different point. Different point means that, I mean, from this end, it is, I mean, this much. Whereas, in this pointer, from this end, it was that much. I hope you can see the cursor. If not, please let me know. So here now is the equivalent of 25 volts. So now if I look at the output side, I mean, the output is actually going to give you the difference in equivalent voltages of the two pointers. So over here, 75 volts minus 25 volts is going to be given by this, that is 50 volts of error. Now this, of course, I mean, whatever we are obtaining at the output side, is indicated with proper polarity. What I mean is that instead of 75 volts over here, if we had 25 volts, and instead of 25 volts over here, if we had 75 volts there, then we would have still got 50 volts of error at the output, but the polarity, the plus minus, would have been reversed, right? So that is what is indicated on the second diagram, the right hand side diagram. You can see 95 volts and 75 volts, which is going to give you 20 volts. But in this case, since this is more compared to the other one, this has a positive polarity. This end has the positive polarity. You can see that by means of this very simple error detecting device, that is a potentiometer, it's going to act as it's going to give you a voltage at the output, and the voltage is going to be proportional to the difference in between the two positions of the two pointers, right? So let us see what's written over here. A pair of potentiometers connected in a bridge circuit. So, I mean, when we say a pair of potentiometers, basically a pair of resistances connected like this, like a bridge across the same source of voltage is what we are indicating. It provides an error voltage whose magnitude is dependent on the difference in position of the two sliders. Okay, so it is the difference in positions, not the absolute position. Absolute position we had when we had a single potentiometer element, as shown in the previous slide. But here we have two elements. So here the difference is what we get at the output, as I have actually explained. Now we come to a particular diagram which shows us, okay, before that, the reference you can see is from the book by Professor S. Dasgupta, Sushil Dasgupta's book. So, of course, if you don't have a hard copy, it's not available as a soft copy. So, you will not be able to refer to it unless you go to the library sometime or the other, maybe when everything opens up, whatever. So, the entire diagram is given over here, the schematic diagram actually. I'm saying schematic because you will see that some things are not exactly drawn, as they should have been, but it's, sufficient as an indicative diagram or representative diagram, right? So, say for example, over here, what we are using is this is the dotted portion over here is giving us the error sensing transducer. So here we can see the source of EMF is indicated by E, and the two elements are given over here. Resistive elements are shown, this one and that one. We can also see the two pointers, and the pointers are actually generating a difference of the two voltages. A difference of difference, which is going to give us a voltage at the output side. That's this one. which is the difference of the two displacements. However, in this particular diagram, though a straight line element has been shown over here, what we are dealing with is angular rotation. So basically, I mean, if I would have, I mean, sort of tried to draw it exactly as it should have been instead of just a schematic, I should have drawn a, um, I should have, or I mean, this book should have rather drawn a circular element over here and over there. But anyway, you can understand that theta r is what is written over there at the shaft of this pointer, shaft to which this pointer is connected, and theta c is what is written over here. This one is what is written at the in the shaft of this pointer, the second pointer given over here. So now basically what we are going to get at the output side over here is going to give us a voltage which is proportional to the difference between theta r and theta c. So this I mean, voltage at the output of this error detector or error sensing transducer is going to be equal to some constant into theta r minus theta c, right? Now over here you can see theta r actually corresponds to what we call a reference shaft or command shaft. So the reference input will be given over here. Maybe we want some degrees or something like that. It's going to be either in degrees or in radians, theta r. And now this element is, however, connected to it is acting as a feedback. So more about that in a moment. But if we, I mean, see, look at the output of this element, it's this element, we find that that is going to be a voltage which has been generated and that is proportional to theta r minus theta c. So that voltage is being applied at the input of this amplifier, an op amp maybe. Op amp gain is indicated over here, and then the op amp is exciting a motor over here, right? So we will actually do a bit more of, I mean, such systems in a bit more of detail as we go by, maybe at the next class or the class after that. But I mean, for the present, it would suffice just to look at the schematic diagram and understand, I mean, from which form, what form the change is taking place to which other form and so on. So that would be what we would stick to for this particular class and this diagram. However, we will be doing such systems in details. We will actually be deriving the model of such, I mean, a similar sort of system. But right now, I am not going into the details of that. So the output of the amplifier, now amplifier also you can see, I mean, the connections exactly are not shown, but what we are showing over here is that there will be a voltage which is going to excite the armature of the motor, and that voltage will be equal to Ka into the input voltage which is being applied to the input of the amplifier, right? So that voltage is going to excite the your motor over here, the armature of the motor. You can also see the field drawn and field current is constant, that's written over there. Not much more of details at this point. We'll do it as I told you. And the shaft of the motor is connected to a gear train, and via that gear train, it is connected to the load. So this is this particular, I mean, this along with this one is the assembly, which is indicating the load. So this is the load shaft over here, and the displacement of the load shaft is indicated as theta suffix c. So if there is a particular displacement over here, or rather, let me come to this point, come back over here. If there is a reference input that we have applied as theta r, I mean, we expect that the output shaft will follow the input angular position. So theta c should ideally be equal to theta r, right? Now, this shaft, output shaft or load shaft as we call it, is connected via a mechanical coupling to this pointer of the potentiometer, such that now the, I mean, say the situation under which theta c becomes exactly equal to theta r, what will be generated, what will be the voltage generated at the output side? It's going to be proportional to theta r minus theta c, which is going to be equal to 0 when theta c is exactly equal to theta r. So that will actually be applying a zero voltage over here, and hence, I mean, a zero voltage will be applied to the motor. So no further rotation will take place once the load shaft is exactly, angular position is exactly equal to the command shaft angular position. However, as long as there exists a difference in the angular rotation, between the load shaft, that is theta c, and the command shaft or reference shaft, which is theta r. As long as the difference exists, a proportional voltage will be, generated over here, and that will take corrective action such that the theta c position, angular position changes, right? So that is the way it is going to act. The moment, as I told you, load angular position becomes equal to your theta r, the corrective action will stop. That will be the position where it's going to remain unless, there is a further displacement which is, being applied at the command shaft or something. Now, as far as the mechanical coupling goes, it is shown by a dotted line, and the coupling is such that the difference in between these two are going to be taken. So that will be done via, the mechanical coupling, so that somehow we are able to get the difference, or rather the voltage proportional to the difference at the output side. So that is going to be taken care of by the mechanical coupling. So here now, in this particular mechanism, this is called a servo mechanism. As I told you, we'll be doing a bit more of this in details as we go by. And here, this is a servo mechanism employing a DC potentiometer bridge. So this, dotted box over here is the potentiometer bridge, of course DC, and it is the potentiometric bridge arrangement that we are referring to. So here, this potentiometer is acting as an error detector. So if I were to ask you to draw the block diagram, the error sensing transducer or error detector would be drawn. You have a reference input, and then you have some other elements in the forward path, and then the output or the load, right? And then there is also a feedback which is coming in, and that is going to, if you draw the, if you recollect how we indicate the error sensor, basically by means of drawing a circular element, and a cross sort of symbol where inside we write the plus and the minus. So basically over here, the feedback is going to be negative in nature, that has to be indicated, whereas this is going to go to the positive side. So as far as this diagram is concerned, just a bit more of detail as far as applicable over here, but nevertheless, we are not going to do the overall model derivation at this point. We'll do it, as I told you, a similar system we'll be doing later. Later means maybe in 1 or 2 classes. So here now, if you look at this diagram, you find that the error voltage, now which is the error voltage? Error voltage is this voltage which is being applied at the input of the amplifier. So the error voltage will be proportional to theta r minus theta c. So that is what is indicated over here. And what would be the constant of proportionality? It is going to be the applied voltage by the maximum displacement, angular displacement, which would have occurred. So E by the maximum displacement multiplied by the difference in the displacement is what is going to give us the error voltage, small e, right? So it can also be written in this form, that is some constant into theta r minus theta c, because the maximum displacement which can take place is constant, it's fixed. The positions that we have as theta r and theta c, those are going to vary, those may be vary, but the maximum which you have over here in these elements, that is theta m, is going to be it's going to remain a constant. So E remains a constant and theta m also remains a constant, as a result of which this can be called a constant, small k, which is this. Now, theta m is the maximum angular displacement of the wiper. Okay, the pointer, as I have been referring to it, is also sometimes called a wiper. Okay, so the same thing is being referred to as a wiper. Now, the maximum angular displacement is theta m, and theta m can either be given, because it's an angular displacement, maximum angular displacement. Theta m may be, the units may be in either degrees or radians, but whatever it is, you have to specify whether it is in degrees, whether it is in radians, because naturally, a conversion has to be done if necessary. Now the sensitivity, okay, so now this constant K is also said to be, it is defined as the sensitivity of the error sensor. So constant K is called the sensitivity and is given by E by theta M. So now if it is given by E by theta M, what would be the units? It is the unit of K, that is the sensitivity, is either volts per degree or volts per radian, because we have E by some theta, that is theta n. So that is volts per degree or volts per radian, depending on whether my theta is indicated in degree or radians. So the error voltage applied to the amplifier, that is this one we are referring to, has a magnitude and polarity determined by the relative position of the command shaft and the follow-up shaft. So what we are saying is that this is the command shaft or the reference shaft, and this is the follow-up shaft. Why follow-up shaft? Because it is actually following the angular position displacement of the load. So it's following it. It's called the follow-up shaft. So now the difference in between theta r and theta c is going to generate E, and with proper polarity, meaning that if theta r is greater than theta c, this side will be positive, this side will be negative. If theta c has exceeded theta r for some reason, then we will have the positive polarity on this side and negative on that side. So with proper polarity, we will be getting the error voltage at the output that is going to be proportional to the difference, and with proper polarity, as I told you. Now, depending on whether the error voltage, that is this one, is positive or negative, we will have the output of the amplifier is also a voltage, and that's going to be the output voltage is going to be given by Ka into the error voltage, whatever it is. If it is small e, then the output voltage over here is going to be Ka into small e. So now this voltage is going to drive, it is actually, applied at the armature, right? Terminals of the armature, which means that that is the voltage which is going to drive the motor, right? So, insofar as this, error voltage is positive, maybe the motor was rotating in one direction. If the error voltage polarity changes, the motor will start rotating in the opposite direction. And if the error voltage is, the generated error voltage is zero, then the motor will not be excited by any voltage, so there will be no further rotation, right? That is the way it works. So depending on whether the error voltage is positive or negative, the motor will rotate in one direction or the other, right? The The mechanical couplings to the follow-up shaft is such that the shaft rotates in a direction which reduces the magnitude of the error voltage, which actually implies a negative feedback, as I told you. So basically, the whole arrangement will be such that if there is a mismatch between these two, a difference is going to be difference in between these angular displacements is going to be the driving factor. So that if, that is the way it is done. The mechanical coupling should be such that it is going to be reducing the magnitude of the error voltage. Error voltage means that this is the error voltage that we are referring to. Error voltage will be large if there is a large difference between theta and theta c. It will be small. Error voltage will be small if there is a small difference in between theta r minus theta c. If the polarity is reversed meaning that if theta c becomes larger than theta r, then opposite polarity will be induced at the output of the error detector, which is going to rotate the motor in the opposite direction, and that is the way it works. Also, the mechanical coupling is such that, the difference is what we will be getting. The voltage at the output will be proportional to the difference only. Now, of course, some things which I've already verbally stated, but I'll just read out from here. So when the follow-up shaft has reached a position corresponding to the command shaft, what will happen? Theta r is equal to theta c. The error voltage will be zero and the motor will stop. So I've already told you that. I hope you've understood. If not, you can interrupt me and ask me. Uh, since the response time of the system can be made relatively short, the follow-up shaft will follow almost any movement of the command shaft. So, if whatever components go inside, if we are able to make the response time small enough, then if we are applying a particular theta r, then theta c will closely try to follow it, because as long as there exists a difference in the angular positions of theta r minus theta c, there will be a corrective action, because as long as the difference in the angular positions exists, that is going to continue, including, correcting if the theta c has overshot. The moment theta r becomes equal to theta c, then the uh, corrective action stops. That's one thing. Another thing is that if the time of action, response time of action, you are able to make the response time of this system small enough by some sort of design. In that case, what will happen is, if I say, for example, put say 10 degrees over here in theta r. So that's the, I mean, after some overshoots and undershoots, close bracket to 10 degrees. Now, say for example, I want the theta r to be equal to 25 degrees. So I change theta r to 25 degrees. Again, then a difference in between these two positions is generated. That is, the difference in the angular positions theta minus theta c has been will be generated. As a result of which, again, the corrective action will now try to bring the theta c to the 25 degrees. So if the response time is short enough, and if the theta r is actually gradually changed, theta c will exactly try to follow the theta r as precisely as possible. Of course, the design of the system has to be done accordingly. As I told you, we will be uh, we also will be looking into, but not not at this point, because most of this will be a repetition of what we have already verbally stated, but I'll read through this anyway. The output shaft can be coupled to the load. That is, I mean, this one sorry, output shaft can be coupled to the load to be positioned, and the dial can be attached to the command shaft. So, I mean, dial being attached to the command shaft means you can have, I mean, sort of a circular disc which has markings, dial as we call it, attached over here, so that you can say, okay, I put 10 degrees over here, so I somehow rotate it to 10 degrees and stop it over there and see whether the output shaft is following that. Again, let us say we want it at 15 degrees, so again, and the dial is then, I mean, positioned at 15 degrees, and we see whether the output shaft is following, and so on. It is done. So the load will then automatically assume the position to which the command shaft is dialed, right? Any deviation from this position will produce an error signal which will initiate a corrective action. So as I told you, the moment the difference between theta c and theta r, there will be a corrective action which is going to keep on taking place. This type of remote positioning is used in radar antennas. We'll actually be doing a remote position control system just after we complete another components, the motors, which we'll be doing in the next class. But this sort of application, or this sort of system finds application, actually finds application in frequency which is used in antennas. So in that case, let us say that there is a target in the sky, which and for which you need to position your shaft of the radar antenna at, say, some angular I mean, displacement. Let us say that, I mean, right now you see that basically your target is positioned such that you need to put your radar at 55 degrees with respect to the horizon. So you dial in 55 degrees over here, and then you have to wait, and in no time, if the system is fast enough, your radar antenna is going to point to towards the. Now let us say that if the target is a moving target, and it has now shifted to, from 55 degree, it has now shifted to the 62-degree position. So again, the operator will make a change in the command shaft position, and accordingly the load shaft will follow, right? So this is, of course, a very sort of, you can say, a basic system that I've tried to describe. Basic in the sense that you're, I mean, saying that manually your this angular shaft position is being changed, and accordingly the command, sorry, the your output shaft or the load shaft is following the command. So in any case, if that is the way it is done, you would be able to use such a system for remote positioning, which is used in meter antennas. Now we come to something which is known as resolution of a potentiometer. So nowadays, of course, all of you are familiar with this term resolution, maybe in a different context, but resolution of screen and images and all that you are familiar with. That matter, we can we can actually uh, sense by using a particular potentiometer. That would be called the resolution of a potentiometer. So it determines the minimum value of input signal that can be represented. So what that means is that, okay, just look at this diagram. It is a very crude and hand-drawn diagram, but you can see here I have shown E, which is the applied EMF, and it's being applied across this point and this point of the circular element. This is a resistive element. Actually, I've tried to show the coils over here because it is going to be coiled in nature. The right hand side diagram shows you the same, I mean, thing, same, you can say the diagram indicates the same device, but here it is actually a photograph which has been, can the reference be seen? But anyway, it has been taken from uh, some website. Now here you can actually see that the coils are wound on this. There's a core over here and they are wound. You can see the windings like this over here. And also in this diagram, you can see the slider. So this point over here is important. So let us say if this is the reference side, how much angular displacement you have from this point to that point is going to be given as the output. The output voltage will be proportional to that, I mean, uh, angular displacement, right? So coming back to my sketch over here on this side, you can also see the slider which is being positioned. Now, whenever you have windings like this, or for that matter, like this over here, there will be, I mean, a finite thickness of the wire will be there. So as a result of which you cannot really expect that the slider is smoothly going to give you the voltage at the output. The output voltage is not going to be smooth in nature. So you can have the slider either pointing to the middle of this winding, this coil, this, I mean, winding, you can say, and or you can have the pointer pointing towards this winding, that is this coil, I mean, right? So there is an angular difference between these two. And now if, say for example, this is, say, let us say this is 2 degrees, okay, just as a trivial example, if this is 2 degrees, so the minimum displacement, angular displacement, which can be indicated by using this sort of, this particular potentiometer, is going to be 2 degrees. I cannot, I mean, indicate a displacement of, say, 1 degree, or for that matter 0.5 degree, by using this particular potentiometer, because physically it is limited by the angle, I mean, by the minimum angular displacement which it can indicate, and that is known as the resolution, right? So resolution determines the minimum value of the input signal which can be represented at the output side. It is determined by the minimum amount by which the resistance between the slider, that's this one, and one end of the resistance element can be changed by rotating the shaft. So as I told you, you can point either over here or there. But I mean, intermediately, if you have some angular displacement which, I mean, demands a smaller value to be represented at the output side, that will not be shown at the output side. So in effect, the output side will have a voltage which is sort of stepped in nature. It's going to follow a step-like nature, because you can, as I told you, if this angular displacement is 2 degrees, so you will have, say, 0, 2, 4, 6, 8, and all that. Those values are going to be indicated at the output side, but nothing like, say, for example, 3 degrees or 3.5 degrees or 7.25 degrees. So basically, the output is going to be limited by the minimum amount by which this change can take place and generate an equivalent output. In wire wound pots or potentiometers, The minimum resistance change is determined by the size and resistivity of the resistance wire and by the length of each turn. So basically, I mean the minimum resistance which can actually be indicated at the output side when you have wire windings like this one, there is a limitation, and the amount is going to be determined, amount meaning the resolution value is going to be determined by the size of the resistance, size of the coils, the resistivity of the resistance wire, and by the length of each turn. So basically, those are some of the factors which would be determining the, how small or how big your resolution is. So, uh, continuing on that, resolution determines the minimum value of the input signal that can be represented, right? So if say you have the shaft angle on this side and the resistance is plotted on the other side, then basically you see that shaft angle can be continuously, changing in a continuous fashion, right? So it can be 0 and it can be 0 0.1, 0 0.2, 0 0.3, 0.4, 0.5, 0.6, etc. But I mean, as I told you, say for example, it is the shaft angle is 1 over here, and here it is, say, how much is it? Let us say this is 3 over here. Now we find that from the, when the shaft angle is 0.5 and it changes to okay 1 and 1.1 or something, then there is a step change in the output that is going to be proportional to the change in the resistance, because at this point you have a particular resistance. If you calculate from the reference side, the moment your slider goes to the next point, here and there, there is no continuity in the sense that that much extra amount has come in. So the change will be, there will be a jump at the, as far as the resistance is concerned as well, right? So it goes from one turn to the next turn, and then till it again goes to the following turn. Basically, the value of the resistance remains the same. So that accounts for this constant portion where there is no further change till again a particular angular displacement is exceeded, where again there will be a jump. So you find that there is actually a dotted element which is shown over here. It's a thin line but shown with dots. That is the ideal element that we would want. Basically, ideal sort of characteristic, which actually is going to be a linear characteristic. You remember that term that we had studied. The dotted one is going to give us a linear characteristic, which is a linear characteristic in between the resistance that is going to be dictating your output voltage and the input side, that is the shaft angle, how much of displacement in the shaft is there. So the dotted characteristic is the linear one, whereas the actual one is the red stepped characteristic that you see over here. So of course the resolution will be determined by the size of the steps. The next diagram actually shows us something which is similar but on a different axis. So displacement, meaning the angular displacement, of course, is on this side, whereas here we directly show the EMF, right? EMF, of course, is going to be proportional to the resistance as we stated. So as far as the characteristic is concerned, it's going to be similar. The only thing is that here we can actually indicate the minimum amount of change in the voltage that is going to be uh, that we are going to be able to get. So delta E is the minimum amount of EMF, which I mean EMF change, which can be indicated at the output side, which we are going to see as a change in the output side. So basically, these steps, this characteristic is the purple one over here, the step one is the actual characteristic, whereas the dotted characteristic is the ideal one. If there was smooth variation in the output voltage as a result of changing the slider position, then we would have got the dotted characteristic, but not in the actual case. We cannot get it. In wire wound potentiometers, at least, we cannot get it. Okay, let us read through this. So the slider moves in succession from one turn to the next as the shaft is rotated, and the resistance between the slider and one end of the element will change by an amount equal to the resistance of one turn of wire. So this much amount will automatically change at one go. Then it's going to remain at that value. Again, it's going to just change to a different value. So this, I mean, the size of this is going to be the amount of resistance change which takes place from, I mean, one position of the slider to the next position of the slider. So the resistance in the wire, the difference in the resistance in the wire will be what we actually will be having as the step sizes in this particular plot. Since the resistance changes by discrete amount as the slider moves from turn to turn, the resistance changes in a stepwise fashion. Okay, I think I'll do this. This is actually what we call voltage regulation, sorry, resolution. So there is actually the resolution that we've studied. We have just, I mean, um, we have studied what resolution means, but as far as, I mean, sort of mm, getting an expression for the same, we have not yet done. So resolution actually is defined in two ways, as we will see, one of which is known as the voltage resolution. So as far as voltage resolution is concerned, voltage resolution is defined as the voltage per step, that is voltage change per step, delta E, divided by the total excitation voltage, which is going to be E. So voltage per step by excitation voltage into 100. So over here you can see delta E by E into 100 as a percentage will give us our resolution, right? Now, as far as delta E goes, delta E is if we have, say, a coil which has smaller number of turns, then how much will be each of these delta E values? Total voltage which is being applied by the total number of turns is going to give us the size of each step over here, the step voltages. So delta E is replaced by E by N, which is the total voltage applied by the number of turns in the potentiometer. That divided by E into 100% is what is going to give us our voltage resolution, right? So if you see in the numerator and denominator, both the E's cancel out and we are left with 100 by N as a percentage, right? So though the term is defined as voltage or yes, the terminology which is used for defining this is the voltage resolution. As far as, I mean, the expression for voltage resolution goes, there is no, I mean, term containing voltage. So whatever be your source of the excitation source of voltage, how much amount we have over here, the voltage resolution is going to be independent of that, right? So if we have the potentiometer or potentiometric error detector actually say excited by 50 volts and having, say, your okay, 100 turns, and if we have the voltage of excitation, say 120 volts, and we still have again 100 turns, then the resolution of both of those are going to be 100 by N, which is 100, I said, 100 number of turns. So the source of voltage, the resolution is not going to depend on the amount of the excitation voltage. It is independent of the amount of excitation voltage. It depends only on the number of turns, right? Now, typical values of resolutions for potentiometers designed for servo applications are generally in the range of, you can see, 0.005% to 0.5%. Those are typical values. Now, as far as resistive elements go, we also know that carbon is often used as a resistive element. So, in potentiometers as well, carbon elements are used. So in carbon pots, because there are no wires, discrete wires are not there, but still we have the resistive element as a continuous carbon element, the resolution over there is 0. So it is as if in a carbon pot, you have the characteristic will be more near to the dotted characteristic that you see over here. That is, the size of the steps is going to be almost very, very small, or I mean, there's no, it's going to tend to 0. That is, this characteristic, the dotted one, that is the straight line characteristic, is the one which is going to be valid for a carbon potentiometer. And consequently, the resolution is going to be equal to 0. Uh, okay, so there is another, type of resolution which is often defined. It is known as the angular resolution, numerically equal to the total winding angle divided by the total number of turns, and therefore expresses the number of degrees of shaft rotation required to produce a one-step change of the output voltage. That is to move the slider from the center of one turn to the center of the next turn. What we are saying over here is that the angular resolution is numerically equal to the total angle winding angle divided by the number of turns. So let us say if we have a 2000 turn resistance element, and that extends over 320 degrees. So the circular element actually, you cannot have 360 degrees being covered, right? It's going to be definitely, whenever we have angular potentiometers, the angular span is going to be lesser than 360 degrees, more like 320 or 310 or something like that. So let us say for this particular numerical example, the angular span of the potentiometer is 320 degrees, and the number of turns which are accommodated within those 320 degrees is given by 2000, that is 2000, right? So that now the angular resolution will be the total angular displacement which is possible divided by the total number of turns, which is 2000. So it will be 320 by 2000 degrees per turn. So whatever value we've got, degrees per turn is the value of the angular resolution. So basically, for this definition, that is for angular resolution, the not only the number of turns is of importance, but the total span of the resistive element, angular span of the resistive element also has to be taken into account for this particular definition. Now, if we want to increase the angular resolution, how can we do it? Naturally, we can, increase the number of turns, because it is the, you have the angular span by the total number of turns, right? So angular span, let us say we've taken 320 degrees. So you cannot actually increase the angular span beyond, definitely not beyond 360, and somewhat lesser than that is the ideal case that, not ideal, the actual case that you would be encountering. So angular span, you really cannot, extend beyond a particular value. At the most, okay, you can say, okay, man, I want 340. Okay, fine, 340, fine, but not beyond 360. So what can you do to improve your angular resolution? Improving means making the resolution smaller. So that means that we would be going for increasing the number of turns. So how can we increase the number of turns? There are, of course, some ways by which the number of turns can be increased. Let me just show you. Okay, this diagram I think would be sufficient. This is a diagram I usually draw on the board and show. Now let us say, okay, from here to there, the total span, angular span is 320 degrees. Okay, like the numerical example that we saw. Now, if you want to increase the number of turns, how can you increase the number of turns? Definitely you want to pack in more number of turns over here. So what would, how can that be done? One way could be to make the wire thinner, in which case you will be able to, put in more coils over, more turns over there, right? What will happen if the wire is thinner? If I take a thinner wire, what will happen? Can anybody try to tell me, if I take a thinner wire, what will happen? This is a resistive element, mind you. Huh? So what will happen if I use a thinner wire?
Mom, it can't carry larger amount of current
Why?
because it has a greater probability of getting burned.
Yes, burn means yes, there will be larger amount of heating, isn't it? Thinner wire means basically your resistivity is going to increase, and as a result of that, heating will take place, and as naturally, as you said, ultimately it may result in burning. So I cannot, I shouldn't make the wires, thinner than a particular limit maybe. So basically, in order to increase the number of turns, increasing the, or sorry, your, uh, yes, increasing the thinness or making the wires thinner, I cannot go beyond a particular, I shouldn't go beyond a particular point. What else can be done? I may say, for example, over here, this is the circular element that you see. Instead of this, I make it larger. So I make, you can see the cursor, I hope. I make the element like this from here to there. Okay, so this is the size of my circular element. So again, over there, I can pack in a larger number of wires, whereas the angular, I mean, displacement still would remain I will keep it at 320 degrees and make the, element larger. But again, I mean, if I make the element larger, that would involve, I mean, a larger length of wire naturally. I mean, first of all, the it is going to become bulky, right? And also, I mean, it will be causing more heating and all that. So basically, there are limitations to how I mean how much I can improve the resolution of my potentiometer. So potentiometer will be physically limited by these factors which are going to govern how less I can make the resolution, meaning how much I can improve it. Uh, okay, so here I'll just try to cover a small portion over here before I end. I'll try to finish off with this potentiometers. Let me see, I think I have one or two more slides, not too many. So linearity of a potentiometer is what we have over here. Now, I mean, this is the shaft angle and the EMF that you can see over here again. The ideal characteristic, as I have stated earlier, is going to be given by the red dotted line, by this one, right? Actually, of course, we see that instead of this red dotted line that is a straight line, we have a stepped characteristic. Okay, but that is not the only thing. Of course, yes, it is going to have a stepped characteristic. Also, what will be having, what will be happening is that because of the physical nature of the wire, it may be that the wire, your wire diameter, that is the cross section of the wire, is not uniform throughout. Okay, so what will happen at some places for the same wire, you are going to have a particular resistance. At the other, I mean, for another turn, the resistance is going to be different, right? So, I mean, that such problems, would be resulting in a characteristic which is a deviation from the straight line one. It is going to actually have something which is different from the straight line one. So of course over here it's a bit exaggerated just for you to understand, but nevertheless the characteristic, the actual characteristic will not be a straight line, but it's going to be something different because of physical factors. What are the factors that, I mean, the linearity depends on? Let us see. Nonlinearity may occur due to non-uniformity of the diameter of the resistance wire. So as I told you, one turn, I mean, your resistance will be something. The next turn, because the diameter has changed, change means maybe by a small amount, but nevertheless it's different. So naturally, your, step size also is going to be different. So basically, non-uniformity is going to be resulting in non-linearity. Also, it may happen that there is unequal spacing of turns. So we are actually winding the wires one after the other. Naturally, the spacing of the turns we are assuming is equal, but it's physically or practically never going to be exactly equal. So that is also going to result in some sort of non-linearity. Also, non-identical size of the turn. Size of the turn means how much, I mean, you have that circle and then the next circle. So, I mean, the size of that circle, that is the turn, may, sizes would be varying from turn to turn, right? So all these are going to amount to nonlinearities of the potentiometric element. So that is what has been shown by this blue line or curve over here, of course in an exaggerated fashion, but nevertheless we'll never be able to have the ideal characteristic, which is exactly this one. First of all, the steps will be there, as well as, I mean, some of these factors are definitely going to be there such that you will be having a non-ideal characteristic, the actual one as shown. This slide has the heading disadvantages. Actually, it should be labeled as limitations of potentiometers. Okay, so limitations of potentiometers is what we have over here, some of which we've already discussed. I'll be, mentioning them again if they come. The wires and precision pot are extremely delicate. So as I have already told you a bit, if you want to make the number of turns more, you would definitely want, why you want to increase the number of turns? Because you want resolution to be lesser. Because if you want precision in your potentiometer, precision means what? You should be able to indicate a smaller amount of variation in the input, and that should be reflected on the output side, so that the resolution should be small ideally. Now, if you want to make your resolution small, as we've just discussed, the number of turns is increasing the number of turns is one way. And for that, now, if you want to increase the number of turns, you have to make your wires thinner. So we've already discussed one problem of, making the wires thinner. There is another problem, that is, if the wires are made thinner, then your potentiometers are going to be extremely delicate to handle, very, very thin wires. So, it will be very difficult to handle such potentiometers, which you want to use for precise applications where, precision is of importance. Now, in practice, output voltage is discontinuous, thus deteriorating servo accuracy. So, why discontinuous? We've already stated it's going to be in a step-like fashion, as well as, not going to be exactly linear. So, because of that, the output, voltage is going to be not exactly following the shaft angular displacement as it should be. Output should ideally be proportional to the input, that is the linear, angular or linear displacement of the shaft. But in the actual case, it's not going to be so. So that will deteriorate the servo accuracy, meaning that it's going to be used in some application. Wherever you are using such potentiometers, it's going to deteriorate the accuracy. Next is that relatively great force is required to move the contact arm, and relatively large displacement is necessary for the wiper. So what we are stating over here is that basically, if you want to, let me just show you that this one, if you want to actually, want that this slider should be in close contact with the wires, that is what we want. Because if there is a loose contact, there is no contact over here for some portion, what will happen? We are not going to get any output at all. So we want that this should be pushed against means it should, be making a very good contact with your circular element. But in the process, what will happen if I want this to actually make good contact with the circular element? The amount of force that is going to be required to move it is going to increase, because this is being pressed against this one as per construction, and I have to move it. So basically, that is a problem. Problem means that if it is used in some delicate application where that much of force is not being generated, then the slider will not be moving at all. So that is a, I mean, limitation or disadvantage that we would be having. So relatively great force is required because we want a good contact, obviously. But in that case, basically, large amount of force is required. What is used when displacement is of limited nature? Why limited nature? Because if we have, say, a rotary potentiometer, the maximum amount of angular displacement that can be, expressed is basically lesser than 360 degree. It's going to be 20 or 40 degrees lesser than 360 degree. That is as far as angular potentiometers are concerned. As far as angular, meaning rotary potentiometers, are concerned. As far as linear potentiometers are concerned as well, if we say, for example, I hope you can see the cursor, if we have a linear element which is, say, for example, from this point to that point, and I want a displacement to be expressed which is basically more than that value. So what will happen? If the pointer has to remain between this end and that end, you cannot express a displacement which is larger than this displacement at the output side. I hope you can see the cursor I'm trying to show with the title bar over here. There are left and right hand side limits are there, and the pointer cannot go out of that. So basically, limit protection is essential. If, say, for example, the length over here is, for example, 20 centimeters, and I want to indicate a displacement of 25 centimeters, it will not be possible for me to do that by using this potentiometer. I have to replace the pot, right? So pot is used when displacement is of limited nature, that is, limit protection is essential. Sensitivity is limited because heat dissipation limits use of higher applied voltage, and relatively high gain amplifier is required. So basically, if you recollect, sensitivity is what? Sensitivity is E by theta m, right? So now, in order to increase sensitivity, two options. One option is that we would have to increase the E. E by theta m means E can be increased to increase the sensitivity, or theta m can be decreased to increase the sensitivity. But if you want to increase the sensitivity by increasing the applied voltage, that is, if you apply a higher applied voltage, naturally heat dissipation will be there, much more heat dissipation naturally, and that will actually, I mean, limit you. You will not be able to apply a high as high a voltage as you want to increase the sensitivity. That's not possible, right? So in order, I mean, to get over this difficulty, what is done is that after this potentiometric arrangement, amplifier is used. The amplifier may have a high gain, so that, I mean, if say for example I get a small amount of voltage at the output of my error detector, okay, 0.5 volts. So I mean, I use an amplifier which has a gain of 10. So that amplifies my voltage to 10 volts, and I can drive that. I can use that voltage as a driving force for my motor or whatever I'm using after that. So I mean, basically, um, the sensitivity is limited because of these. And usually what is done is a high gain amplifier is used after the potentiometric error detector. This is unsuitable for systems where extremely small displacements are to be sensed by the transducer for control purposes because of the resolution problem. I mean, it is going to be limited by the value of the resolution that we've already discussed. So these are some of the limitations of potentiometers, meaning that though this is a very simple sort of arrangement by means of which it is a transducer, and by means of which we can apply it to, applications where it is necessary to get the error value. Okay, so as an error detecting device, if you want to apply such potentiometers, yes, it is simple and you can apply it, but nevertheless, there are certain limitations, and that would not enable you to apply it anywhere and everywhere. You have to keep these limitations in mind. So that, I think, is the last slide. Yes, it is the last slide as far as this potentiometer is concerned, this module is concerned. I'll stop the recording. And I'll also stop the presenting.